Welcome to Quantum, a channel dedicated to theoretical physics, with all its rigorous mathematical underpinnings and profound philosophical implications.
Welcome to Quantum. In this quiz-based walkthrough, we're exploring one of the most profound discoveries in modern physics, the quantum Hall effect. As the questions unfold, this narrated summary will guide you through the key ideas behind the integer and fractional quantum Hall effects, and how quantum mechanics gives rise to topology. In a two-dimensional electron gas under a strong magnetic field, a quantum miracle occurs. The Hall conductivity becomes quantized. Chapter 1 begins with the classical Hall effect, electrons drifting sideways under electric and magnetic fields. But in the quantum regime, their motion is no longer smooth. It locks into discrete energy bands known as Landau levels. These levels reshape how electrons organize. Their wave functions stretch across the plane, and the geometry of their coordinates becomes non-commutative. In the integer quantum Hall effect, Hall conductivity appears in exact steps, each a multiple of e squared over 2 pi h bar. Even disorder can't disrupt this. Localized states trap electrons, while extended states and edge modes carry current without resistance. Then comes the fractional quantum Hall effect, a new phase of matter. Here, electrons form a quantum fluid governed by the Laflin wave function. The excitations of this fluid are not ordinary particles, they're anyons, carrying fractional charge and obeying exotic statistics. It's a topological phase, unlike anything in classical physics. In fact, quantum mechanics hides a deeper truth. Geometry affects not just motion, but phase. Chapter 2 explores how topology emerges from subtle shifts in the wave function itself. We begin with the Berry phase, a phase acquired when a system's parameters trace a loop. Then we see how spectral flow links charge transport to adiabatic changes. Flux drives electrons from one edge to another, with no force required. In the Aharonov-Bohm effect, even a region with zero magnetic field affects a quantum particle, because the vector potential can't be fully removed. In ring geometries, this gives rise to quantized transport. On a torus, the Hall conductivity becomes a Chern number, a topological invariant counting how quantum states twist over parameter space. The fractional quantum Hall effect reveals even more. Quasi-holes aren't just excitations, they remember where they've been. Their Berry connection encodes a history of motion, and when one encircles another, the system gains a fractional phase. Here, topology doesn't just emerge, it becomes the operating system of quantum matter. If quantum fields write the laws of matter, topology gives them memory. Subscribe to Quantum to keep unraveling the geometry of the universe, one phase at a time.